Haloalkanes and Haloarenes, starting with the second class of this. Few questions first of all from the nomenclature part. Write IUPAC names of the following. This compound how will we write its name? First of all, we will expand the formula, writing the carbon atom here. Carbon atom will come here. 1, 2, 3, 4 bonds are here, so carbon valency is complete. Even here 4 bonds are here around this carbon, so its valency is complete. Start from one end now, and even here also carbon will come. Starting it from one end, see CH3. Write CH3 first. Next to CH3 is CH, linking with a single bond. Next to CH is a double bond, so write double bond now. Next to this double bond we have this CH, so CH. Next to CH this bond, and now we have CH here. One side of CH is Br, one side is CH3. So try to write the carbon in a straight chain with the CH, and Br we are writing on one side. So if we change this compound to this way, it will be easy for us to write its IUPAC name. Now we know the rules for writing. This is the parent chain and this is a substituent. Now we have to number the chain from that side, which will give the lowest number to the multiple bonded carbon atom. So from left side we'll number this chain. The name of this compound now is, first is the name of a substituent linking with the fourth carbon. So this becomes 4-bromo. Now chain, how many carbon atoms are here? 5, so pent. Then double bond with second carbon atom, so pent 2-ene. This is the IUPAC name of this compound. Same way we can write this compound IUPAC name of this compound. Now parent chain is the straight chain. These two groups Br and CH3 are not coming in this chain, so these are the substituents. Numbering from the double bond side. Name of the compound, write the name of the substituent first in an alphabetical order. So first will be the Br, 3-bromo, and with second carbon there is a substituent methyl, so 2-methyl. Then chain, 4 carbon atoms but, and there's a double bond with the first carbon, so but1-ene is the IUPAC name of this compound. Next, NCERT question, the in-text question in this chapter. Write structures of the following. Now IUPAC name is given and we have to draw the structure of that compound. First is 2-chloro, 3-methyl pentane. To write the structure of this, first we start with the word root. Word root, there are 5 carbon atoms, pent. Pent is a word root, so there are 5 carbon atoms. 5 carbon atoms first we link in a straight chain with a single bond. Ane means there are all single bonds here. Now number this chain from any side, left to right or right to left, from any side. After numbering the chain, now come to these substituents. 2-chloro, with second carbon we attach chloro. 3-methyl. With third carbon we attach a methyl. So now we have used everything written in a name: 2-chloro, 3-methyl, pent and ane. Last rule after this is complete the valency of all these carbon atoms by putting the required number of hydrogen atoms. So this is the structure of this compound. Second question: 1-chloro, 4-ethyl cyclohexane. Starting with this part, cycloalkane part, cyclohexane. Hex means 6, cyclo means in cyclic way, ane means there are single bonds here. So cyclohexane we have drawn. Now number this from any carbon clockwise or anti-clockwise, from any way. I am taking this as first carbon and numbering it clockwise like this. After numbering, now start from the substituents. 1-chloro. With first carbon we have a chloro group. 4-ethyl. With fourth carbon we have ethyl C2H5. Ethyl is there. We have used everything written in a name. And now there's no need to write here carbon hydrogens. In cyclic compounds we can write the bond line formula also. So this is the structure of this compound. Now third question after this is the 4-tertiary butyl 3-iodoheptane. Starting with the word root hept. Hept 7 carbon atoms. Link them in a straight chain with single bond. So hept and ane we have used. Second rule is number the chain from any side, left to right or right to left. Now 3-iodo. Third carbon is iodo group. 4-tertiary butyl. In the last lecture we have done butyl group. This is tertiary butyl group. This group is tertiary butyl. Remember CH3C. This is tertiary butyl. So tertiary butyl group we are linking with the fourth carbon atom. And last rule, complete the valency of each carbon atom by putting the required number of hydrogen atoms. So this is your third question. 4-tertiary butyl 3-iodoheptane. Fourth question. 1,4 dibromo butene. But. 4 carbon atoms. Number the chain. Now there's 2-ene. 2-ene means with second and third carbon. 2 means with second and third carbon we have a double bond. 1 and 4 we have dibromo. 2 Br groups are there. One with the first carbon atom, one with the fourth carbon atom. And our last rule, complete the valency of all these carbon atoms. So this is the structure of this compound 1,4-dibromo-butene. Fifth question. 1-bromo 4 secondary butyl 2-methyl benzene. Benzene, this. Then number it again clockwise or anti-clockwise. Start from any carbon like this. 1-bromo. With first carbon we put the Br. And 4 secondary butyl. With fourth carbon we put the butyl group. Secondary butyl. Secondary butyl is your this group. So this group we have to link with this bond with this benzene at the fourth position. So CH, this is secondary butyl. So this compound is your, and with 2 we have a methyl group also left here. With second carbon there is a methyl group also. So this is 1-bromo-4 secondary butyl 2-methyl benzene. So some questions to practice IUPAC nomenclature and the structures of compounds. Next topic, the main topic of the chapter, methods of preparation of haloalkanes and haloarenes. How we can prepare haloalkanes and how we can prepare haloarenes. The first method is from alcohols. We can prepare these compounds from alcohols. How we can prepare these compounds from alcohols? By reacting alcohols with the HCl or with HBr or with PCl5 or with PCl3 with SOCl2 thionyl chloride, or we can take red phosphorus and bromine or iodine. So taking all these now one by one. First is reacting alcohol. Alcohol in journal is written as ROH. Like haloalkanes in journal are written as RX. Alcohols are written as ROH. Reacting alcohols with HCl or HBr. What happens in this reaction is H takes out the OH, water comes out, and Cl will come in place of OH. So it's RCl plus water. Chloroalkane. What will form here is chloroalkane. Second example, if we react alcohol with SOCl2, which is called thionyl chloride. Thionyl chloride. Now see the products how we get. 1 Cl of thionyl I'm writing here. Another Cl left here I'm writing here. So after taking out the 2 Cl from this, what is left is SO. SO I'm putting up here. See the products now. It's RCl, HCl and SO2. The products are RCl, SO2 and HCl. So we are getting chloroalkane here in this case. Chloroalkanes are formed and these two are escapable gases here. So we get a pure haloalkane here. Next we have third example. If alcohols are reacted with PCl5, phosphorus pentachloride, then what we get, again to understand this I'm dividing it. 1 Cl I'm writing here, another Cl I'm writing here. After taking out 2 Cl, what is left in PCl5 is PCl3. So that PCl3 I'm writing here. The products are RCl, HCl, and here it is POCl3, phosphorus oxy trichloride. These are the products. So we are getting chloroalkane in this reaction. Fourth example, if in place of PCl5 we take PCl3, then main product will be the same, chloroalkane. Byproduct will be phosphorus acid. Phosphorus acid H3PO3 will form here. Fifth is, if alcohols are reacted with red phosphorus in presence of halogen, halogen will be Br or I only. It will be Br or I. So that means it's Br2 or I2. Then we get here Rx. Rx can be Rbr or Ri. This compound will form here. Rbr or Ri will form. These are the reactions to prepare haloalkanes from alcohols. Alcohols reaction with HCl, with thionyl chloride, PCl5, PCl3 and with red phosphorus and halogen. Out of all these, this method, that is thionyl chloride method, this is preferred. Why? because other two products are escapable gases, so we are getting pure haloalkanes by this method. Second method of preparation of haloalkanes and haloarenes is if we react alkanes. This we have done in 10th class also. Alkanes with the chlorine or with bromine. Then the halogen will replace the hydrogen of alkane. In place of the hydrogen, the halogen will come. So we are getting CH3Cl. And this reaction takes place in presence of sunlight or on heating. And reaction will continue till all hydrogens of alkane are substituted by the halogen atom. So again one more hydrogen comes out, and in place of that there is Cl. Again this hydrogen comes out, halogen will be there. This hydrogen left is also displaced by the halogen. Reaction takes place in presence of sunlight or on heating. This reaction we have done in the 10th class also, and name of this reaction is by free radical halogenation. Free radical halogenation reaction. After doing the two methods of preparation of haloalkanes and haloarenes, one question we are covering up here, that is distinction between primary. We know this symbol for primary. This is a symbol for secondary and tertiary alcohols. Distinction means we have three samples of alcohols: primary, secondary and tertiary. How we distinguish between the three, that this sample is of primary alcohol, this is of secondary and this is of tertiary? By doing a test, and name of that test is Lucas test. By doing Lucas test we can distinguish between the three type of alcohols. Lucas test we use a reagent. Name of that reagent is Lucas reagent. What is Lucas reagent? It is equimolar mixture of HCl and anhydrous zinc chloride. Take equal moles of HCl and anhydrous zinc chloride, mix the two, that will become Lucas reagent. Add this reagent to the three samples that we have: primary, secondary and tertiary alcohol. Like this is primary alcohol. We are adding this sample HCl, and here we have anhydrous zinc chloride. That is, we have added Lucas reagent. Secondary alcohol, adding Lucas reagent. Tertiary alcohol, to this also we add Lucas reagent. So in the three samples that we have got, we have added the Lucas reagent. So that sample in which on adding Lucas reagent, immediately we get turbidity, milkiness. Turbidity means milkiness. Immediately the turbidity comes. The moment we add Lucas reagent, there will be milkiness. That sample is of tertiary alcohol. Now two samples are left. We wait for some time. Now in one more test tube, we'll see the turbidity comes after some time. That sample is of secondary alcohol. And the test tube which is left, in which there will not be any milkiness, that means no reaction has taken place, that is of primary alcohol. So if the reaction is so fast that we get milkiness, that is tertiary alcohol. If after some time reaction we'll see the milkiness, we'll see that is secondary alcohol. And if we'll not see any chain, that is a sample of primary alcohol. Now why is it so? In this case, immediately these two are reacting. Water comes out, Cl comes here. So we'll get the chloroalkane quickly here. This compound is milky in color. That is why milkiness comes. In this case also, Cl will come in place of OH. This compound will get. This compound is of milky color. That is why milkiness comes. But the reactivity of this is slow, reactivity of this is fast. While in this case, this is not able to displace it. So no reaction will take place here. So this way we can distinguish between the three type of alcohols doing the Lucas test using Lucas reagent. This clears us one thing more, that tertiary alcohols reactivity is more than secondary alcohol. Secondary alcohol reactivity is more than that of primary alcohols. After this, we have done the two methods of preparation of alcohols. Now the third method of preparation of haloalkanes and haloarenes by electrophilic substitution reaction. When electrophile will substitute, and we know that these reactions are shown by aromatic compounds, by benzene type of compounds. When benzene is reacted with chlorine or with bromine in presence of Lewis acid, anhydrous AlCl3, FeCl3, FeBr3, then the electrophile from here will displace one of the hydrogens of benzene and will substitute that here. So we get chlorobenzene here. And if we are taking Br2, we'll get Br here, bromobenzene. One Cl left here, and the H that comes out from here will combine to form our byproduct HCl. So this way we are getting the chlorobenzene. In place of benzene, if we take toluene, this compound is toluene, and react this with chlorine or with bromine, again in presence of a Lewis acid, anhydrous AlCl3 or FeCl3 or FeBr3, then this already attached group here will decide that where this electrophile will link, at ortho para position or at meta position. CH3, since it is ortho para directing, so this electrophile will link at ortho plus it will link at the para position. So we're getting these two compounds. Name of this compound is 2-chlorotoluene, and this is 4-chlorotoluene. 4-chlorotoluene. This is a third method to prepare the haloarenes. Now moving on to the next method, Sandmeier's reaction. In Sandmeier's reaction, the reaction starts from benzene, diazonium chloride. This compound is called benzene diazonium chloride. Benzene and triple bond and diazo group is there, diazonium chloride. To benzene diazonium chloride, if we add Cu2Cl2, cuprous chloride and HCl, or we can have cuprous bromide and HBr. we will get chlorobenzene, and if we're using this, we will get bromobenzene. Plus HCl and plus nitrogen. Here we'll get plus HCl plus nitrogen. Now see how we get these products. See, this Cl comes here and we are getting the chlorobenzene here in this case. And now we have this Cu2, Cl2. There's no role of this copper here in this case. Actually, this Cl comes here. This Cl actually is coming here. So this is actually this way. This Cl will combine with this and forms HCl, and this nitrogen comes out here. Similarly, if we're taking the Cu2, Br2, Br will come here. So we're getting bromobenzene. And the Cl that comes out will link with this H and forms a HCl and nitrogen as a byproduct. So either we can get chlorobenzene or we can get bromobenzene in this reaction. This reaction is called Sandmeier's reaction. Fifth reaction after Sandmeier's reaction is just an advancement over the Sandmeier's reaction is Gettermann's reaction. In Gettermann's reaction, the advancement over Sandmeier's reaction is if we take benzene, diazonium chloride and react this with Cu/HCl or with the Cu/HBr, we will get the same product, chlorobenzene plus HCl plus nitrogen, and in this case also we are getting the bromobenzene plus HCl plus nitrogen. See, in this case, this Cl will come here and this becomes chlorobenzene. This Br comes here and we get bromobenzene. Nitrogen comes out, nitrogen, nitrogen. This Cl left here will combine with this H, HCl. Cl combines with this H, HCl is there in this case. So chlorobenzene and bromobenzene. How this reaction is little advanced as compared to the Sandmeier's reaction. Only difference is in Sandmeier's reaction we had Cu2Cl2. Since there was no role of this copper here, so without the copper, when this was used here, Cu was used here, no role of the chlorine here, then the same products were formed. That is why this reaction that was taken by the Gettermann is little advanced over the Sandmeier's reaction. Using these also same products they are formed. So there was no need to take Cu2Cl2, only copper were also giving the same products. Now if we have to prepare iodobenzene, then what we have to do? To prepare iodobenzene, we can get it from benzene, diazonium chloride only, but react it with the potassium iodide and little warm it also. It will form iodobenzene. So this I will link here, nitrogen comes out, and another byproduct is this K and the Cl left here will combine to form KCl. So this way we get iodobenzene. So using the Sandmeier's reaction we can get chlorobenzene, bromobenzene. Using Gettermann's reaction we can get chlorobenzene and bromobenzene. But to get iodobenzene, to benzene diazonium chloride only, we will add Ki and we can get iodobenzene. A sixth method from alkenes to prepare haloalkanes. But further from haloalkanes, there are two methods. First method, by addition of hydrogen halide. Hydrogen halide means HCl or HBr we will take here. Symmetrical alkene. Symmetrical means to the side of double bond we have the same number of carbon atom, both sides are similar. When we add hydrogen halide like HCl, Since it is symmetrical alkene, to any side of double bond H can add, to any side Cl can add. So one side I'm adding H, another side I'm adding the Cl, and double bond changes to single. So what we get here is chloroethane from ethene. So by adding hydrogen halides to the alkenes, we get the haloalkanes. But this is symmetrical alkene. If we take unsymmetrical alkene like propene, if we'll take, this is example of unsymmetrical alkene, because both sides of double bond, equal number of carbon atoms are not there. One side one carbon atom, another side there are two carbon atoms. If we add HCl here, then addition will be according to Markovnikov rule. This rule says negative part of addendum, the adding molecule, will add to that side of double bond which has the lesser number of hydrogen atoms. So Cl will link with this carbon and H will link with this carbon only. It's not at any side any atom will link. If unsymmetrical alkene is there, addition will be according to Markovnikov rule. Second is addition of halogens. Addition of halogens. If to alkene we add halogen like chlorine or bromine, in presence of some solvent this reaction takes place, like CCl4 we use here. Both sides of double bond, one halogen atom will add and double bond changes to single. This product is 1,2-dichloroethane. A vicinal dihalide will form. What is vicinal? Vicinal dihalide means if the halogen atoms are linking with adjacent carbon atoms. If halogen atoms link with the adjacent carbon atoms, that halide is known as vicinal dihalide. Last method, halogen exchange method. Under this we have two reactions. First is Finklestein reaction. This reaction is used to prepare iodoalkanes. Specifically for iodoalkanes only we use this method. So we are taking haloalkane only, and that haloalkane should be chloro or the bromo only. To this, when we add NaI or Ki, there is exchange of halogen exchange. Halogen will exchange here, I will come here and Br will here. CH3 CH2I plus NaBr. So we get iodoalkane here. This compound is iodoethane. This compound is called iodoethane. Second method here is the Schwarz reaction. Schwarz reaction. This reaction is specifically to prepare the fluoroalkanes. To prepare the fluoroalkanes, this method is used. Again, for this, either we take chloroalkane or bromoalkane and react with a compound that has fluorine in it, like AgF, or we can take SpF3 here. Halogen will exchange, F will come here and Cl will come with Ag. This will be CH3 CH2F. Fluoroalkane will form plus AgCl. This compound is fluoroethane. So by exchange of halogen, we are getting iodoalkane and we are getting the fluoroalkane. Name of these reactions are Finklestein reaction and Schwarz reaction.